Welcome to the Silicon Learners. In previous video, we are studying about what is the clock domain crossing, what are the ways to solve it. We are studying about two flip-flop synchronization solution, and we are studying about required and acknowledged handshake solution. In today's video, we are study about the impacts on hardware. Means we are study about the two flip-flop synchro how this two flip-flop synchronization solution impact on the hardware and how it is solved the our CDC problem on the hardware we will cover in the Quartus tool. Okay, the topics covered in today's video is why to flip-flop synchronizer solves the metastability problem, why required and acknowledged handshake is needed for pulse crossing, and we will are cover the one interview question that passing a single pulse from a 100 MHz system to 300 MHz subsystem while guaranteeing safe delivery and preventing data corruption. So in this video we are build FSM that pass the pulse or data from the 100 MHz system to the 300 MHz system without corrupt data, and we are see a proof at hardware level. Okay. So first of all, we are studying out why two flip-flop synchronizer solves the problem. So here you can see why one flip-flop synchronizer will not use for the solve CDC means clock domain crossing problem. So it is causing effect of metastable. In the last video, as I defined, metastable is the output between 0 and 1 where it is caused when output stuck between 0 and 1 means it is the analog state we are considered as a analog state, so that's why we can't use one flip-flop synchronizer. Now why two flip-flop synchronizer? As I tell you, in the two flip-flop synchronizer, flip-flop 1 gets the unstable state which is metastable state. Okay, but and after the one full clock cycle the that state pass to the second flip-flop, and it will be settled in that time period, so that's why we use two flip-flop synchronizer. Key insight is the first flip-flop catches the asynchronous signal, means the message signal, and second flip-flop sample it after one full cycle. So there is the enough time to settle to clean 0 or 1. It will be not stuck at the between 0 and 1, means at the analog state. So you can remember or understand by a simple analogy that one flip-flop is equals to catching a ball with one hand while running, and might it can be drop, and two flip-flop catching with one hand and then passing to the second hand, it is the stable hold. Okay, the first hand means flip-flop 1 may be vowel, but the second hand flip-flop 2 get a stable grip. Okay, so now we analyze the at the hardware this solution. So let's open our project. Here is our waveform file. As I described previous code, same this is the same code. Now we have open our SDC file. Here is it. You can see the script file where we assign the time period for clock A is the 100 megahertz means 10 nanosecond. For the clock domain B, we assign the time period 40 megahertz. Now see this, we assign that the clock A and clock B treat them asynchronous. Now let us see what will be effect of when time twist analyzer will treat them as a asynchronous. Okay. So you can see it is the from a clock A to clock B path as a false path. Now remember our the bad CDC problem means in the CDC problem we can see between from clock A to clock B path there is rise to rise path is 1, but here we can see it is treated as a false path, and this is the actual solution of the clock domain crossing at the hardware level in the simulation tool. Okay, so what is the that false path shows? So it is shows these two blocks means clock A and clock B have no fixed phase relationship, means they are not synchronous, and age can occur at arbitrary times. Now question arises why this is needed. So without this line in the our SDC script, without this line, data launch from clock and must arrive time time quest assume data launch from clock 100, and it is arrive safely into clock 300 megahertz, means here it is using normal setup and hold timing equation, means it is assume all idle conditions, okay, that create impossible timing requirements for asynchronous CDC paths. If you don't declare a clock asynchronous, time quiz try to analyze launch edge from 100 megahertz clock and capture edge from 71.4 megahertz clock. But these clocks are unrelated, and the result causes tons of fair timing violation, negative slack, and meaningless reports. So that's why we set the both domains as a asynchronous, and it is solve our problem. But still this asynchronous path not make CDC safe. It only tells the timing analyzer that do not check timing here. Means it bypass this setup and hold violation. Okay. If you have to do actual CDC solution, you must have to use actual hardware like a FPGA, and you can demonstrate that CDC problem solving on the FPGA. Now let us come on our question, that clock domain crossing pulse synchronizer converting one cycle pulse from 100 megahertz domain to 300 megahertz domain. As you see in the problem, there is first clock domain which is a source domain 100 megahertz clock, and there is another second clock domain which is destination domain, means 300 megahertz clock. The in the source domain, our clock input is 100 megahertz clock, and there is register pulse 100. Okay, this is architecture of the source domain. The architecture of destination domain, we are use two flip-flop synchronizer to avoid the CDC problem. Okay, and at the output logic, we are detect the rise edge, and our output logic is AND get, means synchronous register to AND, not of synchronous delay. Output will be get like this. So here you can see conceptual timing diagram. Now here I mentioned the some questions, the answer of the some important question. First question is why we use two flip flop. So answer is first flip flop may go metastable, and second flip flop gets stable value. Probability of failure or probability of CDC is 0. Another question is why edge detection. The answer is the slow signal held for multiple fast cycle need to generate single pulse and detects 0 to 1 transition only. Another important rule I mentioned, that input pulse must be greater than 1.5 times of slow clock period, means source domain clock. Here 100 megahertz pulse means 10 nanosecond, very greater than 300 megahertz period. Answers captured by fast draw. Now I show you the code. Okay, first of all I will close this time quest. Here is our project. Okay, here is our in the code you can see. Here we define our asynchronous reset. Here is our 100 megahertz source clock and the pulse, one cycle pulse in 100 megahertz domain. It is the destination domain. Okay, and here is we first domain means launch domain code. For the launch domain we define when the reset is low, when the reset is high, or the one cycle pulse in 100 megahertz clock domain will be as it is. Okay, so this is about all code. Now we are look at this code is solves our CDC problem or not. So let us open our script file first. Here is the script file, and you look at the we define again both domain are the asynchronous. Okay, so let us compile our project first and compilation is done. Now we are go at timing quest analyzer. First create timing netlist, second is read SDC file, and now here is you can see from clock 100 to clock 300 between this path it is take as a false path, and this is the way to we can solve the CDC problem in the simulator. Okay, so thank you for the watching this video. In the next video we are discuss about the what is pipeline FSM, and also discuss about pipeline FSM for high speed transaction or a clock. Okay, thank you.